you very much. Again, I'm here to talk about metrology and in particular measurements, and I hope by the end of this presentation today that everybody will be a little bit more excited about measurements and the kind of things they do for our world and our society. Again, measurements have a lot of importance in everything that we do, and the theme at the press summit is, assured optimization and efficiency. Well, measurements do cost money. It does take money to make measurements. Of course, if you want, and that's where the term optimization comes in. Of course, if you wanted to minimize your manufacturing or research and development costs, you certainly could do so without doing any measurements at all, but I think we know what the overall result of that would be. So the end result is optimizing your measurement processes and the costs of manufacturing through good measurements, and the reward out of that is gains in efficiency. If you have a good measurement system, you can have an efficient manufacturing process. You don't have stop ships because you're questioning the quality or capability of the products that you're developing. So, what is metrology? Well, as we've alluded to, metrology is the science of measurement, and it really falls into the spectrum as a subfield of physics. As a matter of fact, the most recent United States Nobel Prize winner in the field of physics, Jan Hall, won his award for building the next generation of atomic clocks. So, and metrology, to use a kind of a new term, is referred to as an infra technology. In other words, this is a science that underpins most other technologies out there. If you think about it, you really can't advance any technology unless you understand the measurements behind that technology. And along that line, and hopefully by the end of this presentation you can understand that Fluke very much is a metrology company. In fact, I'll say that I think that Fluke is one of the best metrology companies in the world. I'm very proud and pleased to be a part of this organization. Much like Jim Caporetto had said, I feel like I've got one of the very best jobs in the entire world, being associated and having the privilege to work in metrology in a company like Fluke. And to that end, the success of Fluke depends on the depth of knowledge in metrology that we possess. And I like to throw up one of my favorite metrology quotes. This one's from Galileo, which is, measure what is measurable and make measurable what is not so. I think that goes to everything that we do in every process in life. If we quantify it, we understand something about it. So, why do measurements matter? Well, the first thing I think that the measurements really come into is fair trade. Metrology is actually as old as civilization itself, because when we were trading an ounce of gold for a bushel of wheat, we wanted to ensure that we were trading not less than an ounce of gold, not more than an ounce of gold, but exactly that amount. And when we received our bushel of wheat, we wanted to ensure that we got the proper quantity of wheat, that we weren't being shortchanged through unfair weights and measures. As a matter of fact, that's why the measurement portion of the measurement keepers in the United States, the National Institute of Standards and Technology, is really, it fits under the Department of Commerce within the United States government. Second issue, safety. I think there are people here in the audience that represent unions and are very dedicated to the safety of their workforce and employees. Safety standards are based upon measurements. You have to know what is a safe amount of voltage to approach and what is a dangerous amount of voltage to approach. You certainly want those standards to be developed with measurements that are accurate and true. Legal requirements. This is definitely becoming a bigger and bigger issue within the world as well. In 2012, the European Union initiated some legislation that requires homes to have an energy performance certificate for their homes before they're allowed to be put on the market. Now, of course, this energy performance certificate involves thermography scans, some of the products that we manufacture. Now, if you start with this requirement of a certificate, I think we could also extend that discussion. It won't be too terribly long that you could understand that if you're rated a Class C versus a Class F, there's going to be a monetary value attached to that, so that measurement. So you want good measurements associated with your energy performance certificate, because it may cost you a lot of money if you don't have good measurements associated with this process. So next things, interoperability. Okay, we're in a global economy now. We need a consistent measurement system around the world. If I wanted to design a circuit board and I wanted to build a board with a 100 ohm resistor, and I found a great supplier in Asia, and I asked them to provide me with 100 ohm resistors. When I get it over here and make measurements, I want to make sure that it's still 100 ohms. So we need a system that we could operate around globally in that process. Traceability. Again, this concept of interoperability depends on all measurements being traceable to a single reference point, which is usually now a constant of nature, and we'll talk about that more in a little bit. And the last thing, of course, consistency and quality. We want industrial control to remain consistent in order to build products with quality. And to that end, about traceability and quality, I've got another little artifact that I wanted to share with everybody today. Since we're looking at one of the Great Pyramids, the Great Pyramids were built through measurement as well. And the measurement standard that they used looked like something like this. This is a replica of the Egyptian cubit. And the Egyptian cubit was based upon the length of the pharaoh's arm from his elbow to the end of his fingers, plus the width of his hand, and that built the cubit. Now, everything that was built in the pyramids was built with a single cubit reference standard. And they had quite a strict quality control program for recalling their calibration of their cubits. The workers were issued usually wooden cubit sticks, maybe the engineers and supervisors were given granite cubit sticks, but nonetheless, every full moon, it was required that all cubits would be returned back for measurement against the master cubit. Now, again, there were consequences to that. Failure to return your cubit back every moon for measurement was punishable by death. So, but end result of quality. The pyramids have equal sides. Yes. The pyramids are built such that their sides are equal to within 6 inches of each other across the pyramids. And if anybody's been to the pyramids and understand how large that is, the relative accuracy of that is approximately 0.05% accuracy, or 500 parts per million is another way to express that. So again, if you think that several thousand years ago, the Egyptians were able to achieve that level of quality that still stands as a testament today, that shows you what good measurements can do. So on to another pyramid, our measurement hierarchy pyramid. And this kind of is a graphical representation of how measurements are disseminated throughout the world. So we start at the SI units. The SI units are the definitions of measurements themselves, the definition of the meter, the kilogram, the second. Of course, the meter now is based upon a natural physical constant. It's based upon the constancy of light in vacuum and the atomic frequency of the cesium atom that defines the second. That's the natural physical constants. And the beauty of that is that you can realize those measurements anywhere in the universe and have traceability back to the SI system. Now, we also have a measurement that's not so traceable, which is the kilogram. And the kilogram is defined as the mass of the piece of platinum and iridium that's locked down in a vault in Paris, France. And everything in the entire world for mass measurements is traceable to this material artifact. And again, we could immediately see the problems with a standard like that. I think we understand the jeopardy that underwent during World War II in those particular years. And if anybody's been reading the newspapers lately, there is some discussion about that over the last 100 years. We think the kilogram is losing mass value, so it's not behaving as a very good artifact for the metrology system. And we're working very hard right now to redefine the kilogram in terms of the Planck constant that will, again, give us a constant of nature. But again, as far as measurement uncertainty goes, of course, the smallest uncertainty starts at the top of the pyramid, and then the uncertainty expands progressively through subsequent measurements. So the next level is the BIPM, which is the International Bureau of Weights and Measurements, the laboratory that we mentioned in Paris, France, that maintains many of the world's laboratory standards. But all in the same plane, national labs, like the National Physical Laboratory of England, the US National Institute of Standards and Technology. And then down to the next level of primary laboratories, such as the Boeing primary lab, where they keep all measurements to manufacture items like the Dreamliner. And then we go further down the chain to the level 1 laboratories, the test laboratories, level 2 laboratories, or level 2 field measurements where we need to make good measurements out in the field. And Fluke plays a part in each one of these parts of the calibration, or in the calibration hierarchy. One of our companies. Fluke Calibration works in the top 3 tiers, and then as we get a little bit more into the subsequent tiers, our Fluke Industrial Groups plays a major role in that, and of course at the bottom of the pyramid, much more measurements are taking place, which are the measurements that you're seeing up here today. But we're going to talk about the top of the pyramid a little bit today too. And along that line, these are some products I'm not sure as everybody's familiar with, but we make some of the world's most accurate commercial products for electrical measurements. So in the DC low frequency range, we manufacture the Fluke 734A. Now this is a precision voltage reference standard, and again, the accuracies we routinely maintain on this is in the order of 0.00003%. And again, we hate saying terms like that. That's too many zeros to talk about, so we use another term, parts per million. So 0.3 parts per million is routinely available, maintained out of this type of a DC voltage reference standard. We also have the world's most accurate AC voltage reference standard, and it's a AC-DC transfer standard. It has operating ranges from 2 millivolts up to 1,000 volts. Frequency response from 10 hertz to 1 megahertz, and it's got accuracies as under 25 parts per million as well. And here's a photograph of the National Institute of Standards and Technology. They are the disseminating body of the DC volt in the United States, and in this picture you can actually see the all of those items on the rack. And let's see here, where's my laser on this one? I should practice this.
I actually can't see
there we go. Here, those are our previous generation of DC voltage reference standards. So from here, all of these products, all of these products, all of these products, all of these products, all of these products are all Fluke reference standards, and those are owned by the National Institute of Standards and Technology. And if you go to any national metrology laboratory in the world, that's pretty much what you see. In fact, on a side note, down there is the old reference standard that these standards replaced, and they turned them off and set them under the bench for storage. They just don't have the heart to get rid of them just yet. Along with electrical measurements, though, Fluke has the world's most accurate temperature products. And to that light, we develop primary temperature standards that realize the international temperature scale through fundamental physical constants. And these constants could be things like the triple point of water, the phase state where water exists in all 3 phases, solid, liquid, and gas. And when you achieve that state, you hit a temperature plateau where the temperature is exactly the same, because all the properties, all of the energy of the properties are changing phase states. So if the system gets a little bit colder, it takes all of that energy, absorbs it into a state change from liquid to solid. If it gets a little bit warmer, it takes the energy and changes it from solid to liquid, but the temperature remains exactly the same, which makes it a really convenient temperature reference. And again, we could realize these temperature measurements down to less than 0.0001 degree accuracy. So metrology in action, what do we do? Well, one of the things that we have to do, of course, is we need to ensure that our traceability to the SI is maintained. That if you buy a Fluke product that's manufactured anywhere in the world, you could use it in any other part of the world and make sure that it works properly. And of course, one of the other issues is we need to make sure that our measurement uncertainty in the calibration process is small enough relative to the specifications that if we say a product meets specifications, that we're correct, that we're producing products with good quality, and you can count on us that those products perform as advertised. We also need to meet measurement quality requirements, such as the international standard ISO 17025, which is an international standard that deals with the competency of calibration and test results, and actually underpins an international agreement for countries to accept each other's test and measurement results from laboratory to laboratory. And as a matter of fact, our service laboratory is undergoing its biannual 17025 assessment just down the street right now. So after this, I hope to run back and check in on that. And then lastly, in order for our products to be accepted by industry, we have to provide publications in peer-reviewed journals about the measurement techniques that are involved with ensuring these products do what they say they do. This is not entirely proprietary. This is where we go into science. This is where we have to have a free exchange of ideas and information, because we have to hold our measurements up to the criticism of the world to ensure that our techniques are sound and correct and valid. And again, in order to have the world's most accurate products, Flukes must maintain some of the world's smallest uncertainties of measurement in that process as well. And the reason that's important, again, is because much of the United States and many countries around the world actually obtain much of their measurement traceability through Fluke. And these are some organizations, just a very small sample, that send their reference standards into Fluke and then disseminate their measurements down throughout their company throughout the world. So one of the products that where we realized the smallest measurement uncertainties, and Jim had mentioned it a bit, this is our Josephson voltage system. Now, the Josephson voltage system makes a voltage reference standard based on constants of nature, those fundamental physical constants that we had mentioned. In this particular one, it's a quantum-based standard based on superconductivity. So you have two superconductors separated by an insulator, and if you bombard them with a known frequency, it will produce DC voltage in discrete quantum steps. And the beauty of that is if you count the right number of steps, you'll get to the volt. So we own a reference standard of that. Again, we're only one of two commercial companies in the United States that owns this system. Everybody else are national government laboratories. But we also routinely verify our measurement capability against NIST's Josephson voltage system. And again, we're achieving uncertainties down around 1.9 parts per billion in that measurement area. And this is an example of the traceability chain of how we get from the Josephson volt down to the products that you know and love today. So we can see that we start with our measurements of the Josephson array at 0.02 parts per million, or microvolts per volt, to our bank of transfer standards that look much like the NIST bank that you've seen in the previous picture. And then we'll characterize a transfer standard, much like our 732 Zener there, that in turn calibrates our multifunction calibrators that provide precise outputs for DC voltage, AC voltage, current, and resistance, all in order to calibrate the digital multimeters that, again, everybody is more familiar with, to ensure that we're meeting the manufacturer specifications for that product. In the pressure, we're also known as a very good pressure company, and again, top of the world in that as well. And to that area, we built a device called the 9607 piston gauge. And this is the heart of that pressure standard. This is actually the piston-cylinder combination that to the left is the cylinder and to the right is the piston, the right is the cylinder, left is the piston. And they realized if you have a known cross-sectional area and you apply a mass load to it, you have pounds per square inch, or kilopascals or megapascals. And again, this product was developed because the National Laboratory of Germany came to Fluke and said that we would like to do an experiment to redetermine the Boltzmann constant and improve the accuracy of the world's knowledge about the Boltzmann constant. And in order to do that, we need about a 500% improvement in pressure measurement capability that anybody has done in the entire world up to this point. And so, can you build us one of these? And Fluke said, well, we'll certainly try. And we spent several years developing this product, and the end result is, yes, we did build the world's most accurate pressure reference standard for this particular experiment, and now we've commercialized that product, and that's available to national labs around the world. And the pressure measurements involved with this product to measure the Boltzmann constant are going to be used to help redefine the SI for the temperature scale that's coming up, anticipated in 2015. And again, here's a photograph of the whole system in action. The piston and cylinder are inside of the automated mass handling system. This is a photograph I took at the National Laboratory of Germany last year, where they had one of the systems operating. And which leads us to infrared measurements. Of course, those are most important to us as well. So Fluke maintains high accuracy transfer radiation thermometers that are sent to the United States national laboratories and the German national laboratories for reference standard calibration. And then from there, we take these primary standards and we transfer their measurements to all of our manufacturing and all of our engineering sites around the world. And an example of that would be something like this, where we send our primary standards out to the National Laboratory of Germany. At a temperature of 100 degrees, our uncertainty is approximately 0.068 degrees. From there, we take and transfer those to our secondary standards in our laboratory. And why do we use secondary standards? Well, that primary standard is a very sensitive device we wouldn't want it to become damaged in any way, because if we were to lose that standard, we would probably be down for maybe as much as 6 months, which would not make our manufacturing team very happy. So we calibrate secondary standards, and at 100 degrees, our transfer is about 0.12 degrees Celsius. And from that, we calibrate transport standards that are transported to all of our engineering centers and all of our manufacturing centers around the world. And an example of that at 100 degrees Celsius, our uncertainty is about 0.20 degrees Celsius. And from the transfer standards therefore in turn calibrate our manufacturing test stations that manufacture the products and provide the final calibration on products. And again, we can provide a transfer at about 0.3 degrees Celsius at 100 degrees in the infrared realm. And all of this is done to ensure that the products that you receive, and this particular one I believe that at 100 degrees Celsius, its uncertainty, its manufacturer specification is 2 degrees. All of this is done to ensure that we have confidence that your unit is traceable and meets its intended specifications. So, in conclusion in this process, one of the key elements of metrology is integrity. If I tell you that my uncertainty at the primary standards level is 0.068 degrees, quite a few people probably can't really do the verification to prove me right or wrong out of that process. So you have to trust me. You have to have faith and confidence that I'm spending day and night, myself, my team, the engineers around the world, are working very hard to ensure that our measurements are correct and true. And why do we do all these things? Because really at the end of the day, we really want to ensure that we earn your trust so that you're confident that our products truly are the most trusted tools in the world. So with that, I thank you very much for your time.
On the last one, there's a jump from like 0.3 to 2.
Yes.
Yeah. Why is that order of magnitude difference?
Oh, that one is because this particular product has a little bit larger uncertainty. We have our point-and-shoot infrared thermometers have much higher levels of accuracy, so as a matter of efficiency, we have to maintain that level to transfer to some of those products that might have a little bit more accuracy. This particular interest, I wanted to give you a real-world example, but you're right. You could say we kind of probably overshot a little bit on this, but it's back to an optimization process. We don't want to have two different processes to realize a temperature scale. So yes, sorry.
Well, the practical application of this is that's what I was sort of getting at too. Obviously, some users are going to have need a greater degree of accuracy, and others not. So, is that standard set for to be optimized for a particular industry, or the?
Again, we have different products, so that we have different levels of accuracy. We have different products for different customers, depending on what level of accuracy that they need. We have some very, very accurate products, and then we have some that are a little bit more field or industrial worthy. So, and the key is that we have to maintain the right measurements for both the highest level and the industrial level. So again, this is a true real world example of how we transfer this process. But if we have another product that's say spec to 0.6 degrees Celsius, we want to make sure that we're right all the way out to the factory floor as well. Does that make sense?
Questions? Other questions?
You're talking about these different levels here. Does this mean that anything that's in the secondary level has been taken physically to where that primary machine is and calibrated and so on down the line?
Correct. It involves the comparison. So we ship our primary standard to Germany or the United States National Laboratory in Gaithersburg for calibration. When it's returned, we have we have what we call our Fluke infrared thermometry laboratory, and that's where we take our primary standards and do our comparisons to the secondary standards in that process. And then we maintain the secondary standards in that laboratory. Then we bring back the transfer standards that circulate back and forth. We may have 2 or 3 that actually go to one particular factory location, so that we're never down because of transport or damage at any one time. But they come back to the standards laboratory, they get calibrated, then they get transferred out to the location around the world. So again, as Jim had said, how we try to have a homogeneous quality system around the world for our manufacturing process. Yes?
Jeff, can you mention any calibration processes today in which the death penalty might be invoked?
It depends on the country you're in.
There you go.
Other questions?
I had a dumb question. That cubit,
Yes.
did each pharaoh have his own cubit?
That is a bit of a problem, but yes, it always went to the king, so they redefined on the new kings. Much like in England, the foot was always defined down the length from the king as well. So it definitely made it a lot more sensible when we moved to the metric system based on the first constant of nature, which was the distance from the North Pole to the equator in a line bisecting Paris, France, back to somewhat of a natural
Okay,
physical
so it did
constant.
vary. So the cubic maker was always hoping the pharaoh died so they get another round of work.
Oh, yes, yeah. And again, in France and in England, even those days, the standards were terrible because the foot, somebody would have an old foot and someone would have a new foot and the old guard. It really made for trade, almost impossible trade conditions. Yes?
10 years ago, thermal imaging was not practical or affordable for most people. What happened in the last 5, 10 years? More and more people can afford the technology. Managed supply or?
Yeah, I think two things, several things in place. Number one, the deflation of electronic manufacturing, much like our DVD players were $300, 10 years ago, and now that you can buy them at Walmart for $10. That goes into it. Competition never hurts, and also scalability. That more people are using them. And so we're able to manufacture more and more and reduce the price. When we were 10 years ago, when they were only manufacturing a few hundred or a few thousand around the world, now we're doing many times more than that as well. And I think that drives the price to the benefit of all the consumers. Yes?
Jeff, how do you determine calibration frequency when you go back to the R level?
Oh, well, maybe we could talk about that a little bit offline, but it's really, we do statistical analysis and process control, and we build control charts with linear regression so that we could look at the expansion of uncertainty over time based on the uncertainty of our linear regression until it gets to a point where we know that that we would like to get a recalibration to confirm our process. And again, we have many check standards in process also to look at drift of products. And even when we send things out to the National Laboratory, before we send them out and when they come back, we verify, we measure them to make sure they didn't get damaged in transport. So all of these statistics go into the analysis of the calibration intervals. But when we develop intervals for products, we like to ensure that at least 95% of the product family, or excuse me, 99% of the product family meet their specifications at the end of the calibration interval. So that's usually our goal that we shoot for. Yes?
Can you say about how much it costs for one of those piston and cylinder pressure standards? Oh,
this isn't a quote, but I think it's that one for the world's best. I think it's up around the 150 area. So again, ballpark in that it's not cheap when you want something that's innovative and groundbreaking and the best technology in the world. I'll say it's not something you can buy at Walmart. So. Other questions? So I will leave my cubit out on the side if you want to play with it later. Thank you very much.
Thank you.